Hello there and welcome to this Sleepy Science channel. I'm so glad you found your way to this video because tonight we're exploring something quite special. The beautiful mysteries that science has not yet solved. Wherever you are in the world, allow yourself to settle into this shared moment of stillness. Dim the lights, get comfortable, and let your body sink gently into rest. For all the wonders we've discovered, for all the questions we've answered, the universe still holds countless secrets. Some mysteries stretch across galaxies and black holes. Others hide in the depths of our oceans, in the quiet rhythms of our minds, even in the cells of our own bodies. These unanswered questions don't represent failures of science. They represent invitations to wonder, reminders that we live in a cosmos far richer and stranger than we yet understand. Tonight, we'll drift through these gentle mysteries together, not to solve them, but simply to rest in their presence. There's nothing you need to remember, no answers you need to find. Just let these questions carry you softly towards sleep, like stars scattered across a peaceful night sky. Each mystery is a doorway to calm reflection, a reminder that the universe still has so much to reveal. Now, settle in as we begin this gentle journey through the beautiful unknowns of science. Perhaps the most fundamental question we can ask is also the one science cannot yet answer. Why is there something instead of nothing? Why does the universe exist at all? Physics can describe how matter behaves, how galaxies form, how stars shine. Cosmology can trace the universe back to its earliest moments. But the question of why there should be a universe in the first place, why there are laws that allow reality to exist, remains just beyond our reach. Some physicists suggest that nothingness might be naturally unstable, that existence could be inevitable in ways we don't yet understand. Others propose that a universe is just one of countless others in a vast multiverse. But these ideas only deepen the mystery rather than solving it. No experiment we can design seems able to measure why being itself emerged from whatever before. This question sits quietly beneath every other mystery. A gentle reminder that the most basic fact of all, that anything exists, remains beautifully unexplained. Think about it for a moment. Right now, you exist. The room around you exists. The earth beneath you, the stars above, the atoms in your body, all of it is here. This seems so ordinary that we rarely pause to wonder at it. But there's no obvious reason why any of it should be. Reality could have remained quiet, still, empty. Instead, here is everything. Philosophers have pondered this for millennia. Why is there being rather than non-being? Science has given us remarkable tools to explore reality, but this question rests just beyond their reach. We can measure the age of the universe, map its structures, understand its evolution, but the why beneath it all remains gently unexplored. Quantum physics offers a curious insight. What we call nothing, the vacuum of space, may not be truly empty. Even in the darkest void, particles might flicker into existence and vanish again, appearing and disappearing in what physicists call quantum foam. Some suggest that perhaps the universe itself emerged this way. The absolute nothingness might be fundamentally unstable, and something must always arise. But this doesn't truly answer the question. it only moves it. Why should quantum fields exist? Why should the laws that govern this flickering exist? The multiverse offers another approach. Perhaps our universe is one of countless others, each with different properties, different laws. In such a vast landscape of realities, at least some would exist simply by probability. We find ourselves in one because only universes with the right conditions can produce observers to ask the question. But the mystery continues. If the multiverse exists, why should it exist? What allows that vast collection of universes to be? Some thinkers propose that existence might simply be the default state, that non-existence could actually be less stable than we imagine. Perhaps reality in some form must always be. That being is more fundamental than nothing. But we don't currently have ways to test such ideas. No telescope can peer beyond existence itself. No experiment can measure the boundary between being and non-being. What makes this mystery so peaceful is its completeness. We're not close to solving it. We're not even entirely sure it can be solved through science alone. It sits at the foundation of everything, patient and quiet. Every star you see, every breath you take, every moment of consciousness, all rest upon this unexplained foundation. Reality simply is, and we are part of it, held gently within existence itself. You don't need to carry this question tonight. Perhaps it never will be answered, and there's something calming about that. To exist within a mystery so vast, so fundamental, is to rest in wonder. You're here now, part of something that continues with perfect consistency. That's enough. That's everything. Let your breathing slow as we drift to the next mystery. We can trace the universe's story back nearly 14 billion years to a moment when everything was unimaginably hot and dense. We call this the Big Bang. But what actually set it in motion? What provided the initial spark that began the cosmos? Scientists have pieced together a detailed history from fractions of a second after the beginning, but the true first cause remains hidden from view. Some theories imagine the Big Bang as a quantum fluctuation, a tremor in reality itself. Others suggest it was one moment in a potentially endless cycle of cosmic births and transformations. The challenge deepens because time itself may have begun with the Big Bang, making the question of what came before difficult to even formulate properly. The spark that set everything in motion, the moment when space and time first emerged, is a mystery that continues to rest just beyond our current understanding, peaceful and patient in its silence. Cosmologists have mapped the universe's history with remarkable precision. We know that about 380,000 years after the Big Bang, the universe became transparent, releasing the light we now see as the cosmic microwave background. We know that within a few 100 million years the first stars ignited. We can trace the formation of galaxies, the birth of our solar system, the emergence of life on Earth. The story is detailed and well supported by evidence, but the very first moment, the trigger itself, remains veiled. What set everything in motion? Why did the Big Bang happen at all? These questions touch the deepest foundations of cosmology, and the answers remain beautifully elusive. One possibility involves quantum mechanics. At the smallest scales, particles can appear briefly from the vacuum, borrowing energy from uncertainty itself. Perhaps the entire universe began this way, a quantum fluctuation that expanded into everything we see. The early universe was so small, so compressed, that quantum effects would have been significant. In such conditions, perhaps the emergence of space-time itself was somehow natural or inevitable. Another idea suggests the Big Bang might not have been the absolute beginning but one event in a longer cycle. Perhaps the universe expands and contracts, each cycle ending in a transformation that seeds the next expansion. In this view, our universe could be just one chapter in a story with no true beginning. Time might stretch infinitely backward and forward, cycles repeating without end. Some theories even propose that our Big Bang could have been the birth of a new universe, inside a black hole from another older cosmos. The compressed region at a black hole center might, under certain conditions, become the seed of a new expanding space-time. If this were possible, universes could bud off from one another like branches on a tree. What complicates all of these ideas is time itself. If time began with the Big Bang, then asking what came before may not make sense in the usual way. Before requires time. Without time, the concept of before dissolves into something our language struggles to capture. Instruments like the Hubble Space Telescope, the Planck satellite, and the James Webb Space Telescope have given us snapshots of the infant universe. We can see galaxies as they were billions of years ago. We can measure the cosmic microwave background with remarkable precision, but none can peer into the first instant itself, the moment of ignition. The spark that began the universe remains hidden, wrapped in a mystery we can approach, but not quite touch. And perhaps there's beauty in that. The universe began for reasons we may never fully understand, and here we are, billions of years later, able to ask the question. The mystery doesn't diminish the cosmos, it deepens it, adding layers of wonder to everything that exists. Nothing to solve right now, just let the question drift past you gently. Every moment slips from present to past with perfect consistency. You remember yesterday, but not tomorrow. A cup falls and breaks, but never leaps back together on its own. Time, in our experience, flows only forward. This is called the arrow of time. What makes this curious is that the fundamental laws of physics don't actually require it. At the smallest scales, equations work equally well forward or backward. Nothing in them demands that time should have a direction at all. Scientists often connect time's arrow to entropy, the tendency of disorder to increase. But this only raises another question. Why did the universe begin in such an ordered state that time could have a direction at all? The one-way flow of time shapes every aspect of existence, yet its origin remains one of science's most peaceful mysteries, a current that carries us gently forward without revealing its source. Time feels fundamental to existence. You've experienced thousands of moments flowing from future to present to past. Each second arrives, exists briefly, then slips away. This progression seems natural, inevitable, yet the mathematics that describe the universe's smallest components are symmetric in time. An electron can move forward or backward through time in the equations, and the physics works either way. This creates a gentle puzzle. If the fundamental laws don't require time to flow forward, why does it? Why can we remember the past but not the future? Why do processes run in one direction, rarely reversing? The answer often given involves entropy, a measure of disorder. In our universe, entropy tends to increase. A broken glass doesn't spontaneously reassemble. Heat flows from hot objects to cold ones, not the reverse. This tendency gives time its direction. We perceive time flowing forward because entropy increases that way. But this explanation only shifts the question. Why should entropy increase at all? The answer seems to lie in the universe's initial state. When the cosmos began, it was in an extraordinarily ordered configuration. All the matter and energy was concentrated, arranged in a specific way. Since then, the universe has been spreading out, becoming more disordered naturally. This raises the real mystery. Why did the universe start in such a low entropy, highly ordered state? There's no obvious reason it should have. A random beginning would more likely produce a disordered universe. The fact that the cosmos began ordered enough for entropy to increase, for time to have an arrow, remains unexplained. Some physicists think time's arrow might be connected to the universe's expansion. As space stretches, the overall entropy can increase, giving time its direction. Others suggest information spreading through the cosmos creates the arrow, with the future being the direction in which information naturally disperses. Quantum mechanics adds another layer. Some interpretations suggest time might emerge from quantum entanglement, from the way information becomes locked into correlations between particles. In this view, time isn't fundamental, but emerges from deeper quantum processes. What remains certain is that we live inside time's flow. Every heartbeat marks its passage. Every memory confirms it. Every plan for tomorrow assumes it will continue. Time carries us forward with gentle inevitability, never pausing, never reversing. The mystery of why time flows in only one direction is something you experience every moment. Right now, this instant is becoming the past. The next second will arrive, exist briefly, and join it. This flow structures everything about existence, yet its origin remains beautifully hidden. The current that carries us is steady and reliable, even as its source remains peacefully unexplained. You can let go of this thought now. Time will continue its patient work while you rest. When astronomers measure how galaxies spin, they discover something remarkable. Stars at the edges move far too quickly. By all calculations, they should drift away into space. Instead, they remain bound, held by something we cannot see. This hidden mass is called dark matter. It neither glows nor absorbs light, making it invisible to telescopes, yet its gravity shapes everything around it, holding galaxies together and bending the paths of starlight. Scientists estimate that dark matter makes up about 85% of all matter in the universe. But what is it? Decades of searching have not revealed its true nature. Perhaps it consists of undiscovered particles that barely interact with ordinary matter. Perhaps it's something stranger still. For now, this invisible scaffold that structures the cosmos remains one of the universe's most beautiful secrets, quietly holding everything in place. The discovery of dark matter came from careful observation. In the 1930s, astronomer Fritz Zwicky studied galaxy clusters and noticed they were moving too fast to stay bound by their visible matter alone. Decades later, Vera Rubin confirmed this pattern by measuring how individual galaxies rotate. The outer regions spin at speeds that visible matter cannot explain. By all rights, stars far from a galaxy's center should orbit slowly, like distant planets in a solar system. Instead, they move just as quickly as stars near the core. This flat rotation curve goes against expectations unless something invisible is present, contributing mass and gravity. Dark matter provides a possible answer. If galaxies are embedded in halos of invisible matter, their rotation curves make sense. The dark matter's gravity holds everything together, allowing galaxies to spin without flying apart. Computer simulations show that dark matter could form the scaffolding along which visible matter clusters, creating the cosmic web of galaxies and voids we observe. But what is dark matter made of? This remains one of astronomy's greatest mysteries. It cannot be ordinary atoms. We've ruled that out through multiple observations. It must be something else, particles that interact through gravity but barely interact with light or normal matter. One leading candidate is called WIMPs, weakly interacting massive particles. These hypothetical particles would have mass and exert gravity, but would rarely collide with ordinary matter. Experiments deep underground have searched for WIMPs passing through Earth, hoping to catch one interacting with a detector. So far, none have been conclusively found. Another possibility is axions, extremely light particles predicted by certain theories. These would be produced in vast numbers and could account for dark matter's abundance. Other ideas suggest dark matter might consist of primordial black holes formed in the universe's first moments, or even exotic particles we haven't imagined yet. Gravitational lensing offers compelling evidence for dark matter. When light from distant galaxies passes near massive clusters, it bends, creating distorted arcs and multiple images. By mapping this lensing, astronomers can measure how mass is distributed. Again and again, they find more mass than visible matter can account for. The cosmic microwave background also bears dark matter's fingerprint. The tiny temperature fluctuations in this ancient light match predictions for a universe where dark matter outweighs normal matter by about 5 to 1. Everything fits together, pointing toward this invisible presence. What makes dark matter a peaceful mystery is its patience. It's been there all along, holding galaxies together for billions of years. It shaped the cosmic structures that allowed stars and planets to form. Without dark matter, the universe would look entirely different. Galaxies might never have formed at all. This invisible scaffold doesn't ask to be understood. It simply exists, doing its work quietly, consistently. We can measure its effects, map its distribution, feel its gravitational influence, but its true nature remains hidden, a secret the universe keeps gently to itself. Allow yourself to simply listen and drift. these ideas can float through your mind gently. In the 1990s, astronomers studying distant supernovae expected to see the universe's expansion slowing down. Gravity, after all, should be pulling galaxies back together. Instead, they discovered something surprising. The universe is not just expanding, it is accelerating, spreading faster over time. Something appears to be pushing galaxies apart, and we call it dark energy, though the name is simply a placeholder for our uncertainty. Dark energy seems to make up nearly 70% of the universe's total energy, yet we cannot see it or fully understand what it is. It might be a property of empty space itself, a kind of energy woven into the fabric of the vacuum, or it might point to physics we haven't yet discovered. This invisible influence shapes the cosmos in ways we can measure, but cannot yet fully explain. The discovery was unexpected. Two independent teams were measuring distant Type Ia supernovae, stellar events that serve as cosmic mile markers. These supernovae have a known brightness, allowing astronomers to calculate their distances. By comparing distance with redshift, which shows how fast galaxies recede, the teams hoped to measure how much the expansion was slowing. The results were surprising. The expansion wasn't slowing, it was accelerating. Distant galaxies are rushing away faster than they should be if gravity alone shaped cosmic dynamics. Something unseen appears to be gently pushing them apart. This mysterious influence was named dark energy, though the name reveals our uncertainty more than our understanding. Dark energy now appears to make up the largest portion of the universe's total energy budget. Normal matter, everything we can see and touch, makes up less than 5% of the cosmos. Dark matter accounts for about 27%. Dark energy makes up the remaining 68%. What is it? The simplest explanation is that dark energy could be vacuum energy, a property of empty space itself. Quantum mechanics suggest that even the vacuum has energy, with particles briefly appearing and disappearing. This energy, spread throughout all space, could create a gentle outward pressure driving acceleration. Einstein's equations actually allow for such a possibility through something called the cosmological constant. Einstein introduced it briefly, then set it aside, later calling it a misstep. But modern observations suggest something like the cosmological constant may be real, woven into the fabric of space-time itself. Another possibility is that dark energy is not constant but changes over time, perhaps through a dynamic field similar to those that might have driven cosmic inflation in the universe's first moments. This would mean dark energy's strength could vary, with consequences we cannot yet predict. Some physicists even wonder if dark energy points to modifications in our theory of gravity itself. Perhaps on cosmic scales, gravity behaves differently than Einstein predicted. This would require rethinking general relativity, one of physics' most successful theories. What makes dark energy particularly mysterious is its subtlety. Unlike other forms of energy, it's incredibly dilute, spread thinly across vast volumes of space. Yet its cumulative effect appears to dominate cosmic expansion. Over billions of years, it has gradually gained influence, overcoming gravity's pull. The consequences are significant. If dark energy remains constant, the universe will likely expand indefinitely, galaxies drifting farther apart until the cosmos becomes increasingly sparse. Stars will eventually exhaust their fuel. The cosmos will grow cooler and quieter, approaching a state of maximum entropy over unimaginably long timescales. If dark energy grows stronger over time, the outcome could be even more dramatic. But this remains speculation. For now, observations suggest dark energy appears relatively constant, at least over the billions of years we can measure. Dark energy is the universe's most dominant component, yet we understand it the least. It shapes cosmic destiny, influencing whether the universe will expand forever or meet some other fate. This invisible influence works patiently, consistently, stretching space in ways we can detect but cannot yet fully comprehend. The mystery remains beautifully open, reminding us that the cosmos still holds secrets far beyond our current understanding. Nothing you need to hold on to, just let it drift. The universe appears balanced on a delicate edge. If gravity were slightly stronger, stars might compress too quickly. If it were weaker, galaxies might never form. Even tiny changes to the fundamental constants of physics could make atoms difficult or impossible, leaving a universe without structure or complexity. This observation is known as fine-tuning. Why should the laws of nature have the values they do? There's no obvious reason why the forces should take the strengths they have. Some argue this could be coincidence. Others suggest countless universes exist, each with different laws, and we happen to inhabit one where life is possible. Still others believe a deeper principle we haven't discovered might naturally lead to these specific values. The question remains open, resting peacefully in the background of existence. The universe feels remarkably, mysteriously suited for stars, planets, and the emergence of life itself. Consider the constants that govern reality, the strength of gravity, the charge of an electron, the mass of a proton, the speed of light. These numbers define how the universe works. They determine whether atoms can form, whether stars can shine, whether chemistry is possible. Change any of them by even a small amount, and the cosmos would be quite different. If gravity were just slightly stronger, stars might burn too hot and too fast, exhausting their fuel in millions rather than billions of years. Planets might be pulled too tightly to their stars, making stable orbits challenging. If gravity were weaker, matter might not clump together as readily. Galaxies might not form, stars might not ignite. The universe could remain a thin, dispersing cloud of hydrogen and helium. The strong nuclear force which binds protons and neutrons in atomic nuclei is similarly delicate. If it were a bit weaker, only hydrogen might be stable. No carbon, no oxygen, no complex chemistry. If it were stronger, hydrogen might all fuse into heavier elements shortly after the Big Bang, leaving less fuel for stars. Electromagnetism must balance precisely with nuclear forces. If electromagnetic repulsion were too strong, atoms might struggle to bond into molecules. If too weak, electrons might collapse into nuclei, making chemistry very different. The range of values that permit both stable atoms and complex molecules appears relatively narrow. Even the ratio of matter to space must fall within certain bounds. Too much matter and the universe might have recollapsed long ago. Too little and galaxies might never have formed. The actual density sits near a value that allows structures to emerge while avoiding early collapse. Why should all these constants have values that permit complexity? This is the fine-tuning question. One answer is chance. Perhaps these are simply the values our universe happens to have, and if they were different, we wouldn't be here to notice. But the degree of apparent precision seems noteworthy. The multiverse offers another explanation. If countless universes exist with different constants, at least some will have the right values for life. We naturally find ourselves in one of those cases because only such universes can produce observers. In this view, fine-tuning could be selection bias. We observe a life-friendly universe because we couldn't exist in any other kind. Others suggest a deeper principle we haven't discovered might constrain the constants, naturally leading them to take these specific values. Perhaps the laws of physics aren't arbitrary, but follow from some underlying mathematical structure. If we understood that deeper layer, fine-tuning might disappear, revealed as somehow necessary rather than fortunate. Some find the fine-tuning observation points toward intentional design, though science cannot directly test such ideas. The question touches philosophy as much as physics. What we can say is that the universe appears delicately balanced, poised in a configuration that allows stars, planets, chemistry, and life. This mystery sits quietly beneath everything. You are made of atoms that exist because nuclear forces have the values they do. You breathe air on a planet orbiting a star that shines because gravity and electromagnetism balance in particular ways. The fact that you can wonder about these questions depends on this balance being what it is. There's something peaceful about living inside this mystery. The universe didn't have to be this way, yet it is. The constants could have been different, yet they're not. Whether by chance, necessity, or something beyond our current understanding, reality arranged itself in a way that permits complexity and awareness. That's enough. That's remarkable. Let your shoulders relax. You don't need to solve anything tonight. The observable universe extends about 90 billion light years across, but we cannot see beyond this horizon. Light from farther regions simply hasn't had time to reach us since the Big Bang. But what lies beyond that edge? Does the universe stretch endlessly in all directions, unbounded? Or is it finite, perhaps curving back on itself like the surface of a sphere? Scientists search for clues in the cosmic microwave background, the faint afterglow of the Big Bang. So far, measurements suggest the universe is remarkably flat. But this doesn't settle whether it continues forever. The true size and shape of the cosmos remain just past the boundary of what we can observe. This uncertainty is strangely calming, a reminder that reality may extend far beyond anything we can measure, quiet and vast in every direction. The observable universe has limits not because space ends, but because light has only had finite time to travel. In the 13.8 billion years since the Big Bang, light could only reach us from regions within a certain distance. beyond that lies space we simply cannot see yet, a cosmic horizon that expands slowly as the universe ages. But does space actually end somewhere, or does it continue indefinitely? This is one of cosmology's deepest questions. An infinite universe would mean space stretches without bound, containing endless galaxies, stars, and perhaps even endless variations of everything that exists here. A finite universe might loop back on itself, so travelling far enough in one direction could eventually return you to your starting point. The shape of space depends on its curvature. If the universe has positive curvature, like the surface of a sphere, it could be finite. If it has negative curvature, like a saddle, it might be infinite. If it's flat with zero curvature, it could be either infinite or finite depending on its topology. Measurements of the cosmic microwave background provide clues. Scientists look for patterns that would reveal curvature. So far, the universe appears flat to within a fraction of a percent. This flatness is itself noteworthy. But flatness alone doesn't tell us if the universe is infinite. If the universe is infinite, then everything that's possible could happen somewhere. There would be countless galaxies, countless stars, countless planets. Somewhere in that vastness, conditions similar to here might repeat. The mathematics suggests that in an infinite universe, there could be many worlds with similar or identical conditions, though infinitely far away. If the universe is finite, then reality has a size, even if unimaginably large. Perhaps space curves back on itself in ways we cannot visualize in 3 dimensions. Perhaps if you could travel far enough, you might eventually return, though the distances would be staggering. Some theories suggest the universe might have boundaries or edges in higher dimensions we cannot perceive. Our 3-dimensional space could be the surface of something larger, curved through dimensions we don't experience. This would make the universe finite yet unbounded with no edge to encounter. The question may never be fully answered. If the universe is infinite, we can only ever observe a finite portion. If it's finite but larger than our horizon, we might never see enough to measure its full extent. The cosmic microwave background offers our best snapshot, but its information has limits. What remains certain is that beyond what we can see lies more space. More galaxies, more stars, more mysteries. Whether that more continues forever or eventually closes back on itself, we rest within a cosmos far larger than we can fully map. The uncertainty about its ultimate size is strangely comforting. Reality extends beyond our sight, quiet and patient, holding secrets we may never fully uncover. Let these thoughts drift past you like a distant starlight. Some of the most successful theories in physics suggest something remarkable. Our universe might not be alone. The concept of the multiverse proposes that countless other universes could exist, each with potentially different laws of physics, different histories, even different numbers of dimensions. Cosmic inflation, the rapid expansion thought to have occurred just after the Big Bang, might naturally create bubble universes. String theory predicts a vast landscape of possible realities. If true, we inhabit just one outcome among many. This could explain fine-tuning. We exist in a universe suited for life because only such universes can produce observers. But there's a challenge. If other universes lie forever beyond our cosmic horizon, we may never observe them directly. The multiverse remains both fascinating and controversial, a beautiful possibility that stretches the very definition of what we can know. For now, it rests as a possibility, peaceful and patient. The idea of multiple universes arises naturally from certain theories. Cosmic inflation, which describes the universe's earliest moments, suggests space can undergo exponential expansion. If different regions of space stop inflating at different times, they could form separate bubble universes, each with its own properties. Our universe would be one bubble in what might be eternally inflating space. String theory, which attempts to unify quantum mechanics and gravity, predicts a vast landscape of possible vacuum states. Each state corresponds to different laws of physics, different particle properties, different fundamental constants. If all these possibilities are realized somewhere, the result could be a multiverse containing many variations. Quantum mechanics offers another path to multiple universes through the many worlds interpretation. Every quantum measurement that could go multiple ways might go every way, with reality branching. Each outcome could happen in a different branch. This would create a continuously branching tree of realities, all equally real, never intersecting. The multiverse offers a possible solution to fine-tuning. If countless universes exist with different constants, at least some will have values that permit life. We find ourselves in such a universe not because it's special, but because we couldn't exist anywhere else. This is called the anthropic principle. Observers can only exist in universes capable of producing observers. But the multiverse is controversial. The central challenge is testability. If other universes lie forever beyond our cosmic horizon, no signal from them can ever reach us. We cannot observe them, measure them, or directly verify their existence. Some argue this makes the multiverse difficult to test scientifically, a speculation beyond the reach of experiment. Others counter that many scientific theories predict things we cannot directly observe, like the interiors of black holes, or the moments immediately after the Big Bang. The multiverse might be a prediction of theories we can test in other ways. If inflation or string theory succeed in explaining observable phenomena, their prediction of multiple universes gains indirect support. The question of whether the multiverse is real touches deep issues about what we can know. If reality extends beyond what we can ever observe, how should we think about it? Is it real if we can never see it? Or should science limit itself to what's observable in principle? For now, the multiverse remains a possibility, neither proven nor ruled out. It offers explanations for puzzles like fine-tuning, but at the cost of introducing vast realms we may never see. Some find this intellectually satisfying, others find it challenging. The discussion continues quietly in physics departments and scientific papers. What's certain is that the idea stretches our sense of scale. If true, the multiverse would mean everything we observe, all 90 billion light-years of observable universe, is just one small bubble in something vastly larger. Reality would extend beyond comprehension, containing many variations the laws of physics permit. You don't need to hold on to these ideas. Let them drift past gently. The multiverse, if it exists, would be patient and silent, other possibilities pursuing their own paths through reality. Whether they're real or not, we rest within our own cosmos, which is wondrous enough. Einstein's general relativity reveals that space and time are not fixed backdrops, but flexible, dynamic. They bend and curve, shaping the motion of planets and the flow of light. But what, at the deepest level, is this fabric made of? At large scales, space-time appears smooth and continuous, but quantum mechanics suggests everything should be grainy and uncertain at small enough distances. Reconciling these views is one of physics' greatest challenges. Some theories propose that space and time emerge from something deeper, perhaps networks of quantum information or patterns of entanglement. In this view, space-time is like a surface, and beneath lies a more fundamental reality we cannot yet perceive. Others wonder if time itself might be more complex than we think, perhaps emerging from deeper processes. What we experience as the stage on which reality unfolds may not be what it seems at the smallest scales. This mystery remains one of the most profound questions about the nature of existence. Space and time feel fundamental. They seem to be the container in which everything happens, the stage on which reality plays out. But Einstein showed this stage is dynamic, not static. Mass and energy curve space-time, and this curvature is what we experience as gravity. Planets orbit stars by following curves through this flexible fabric. At large scales, this description works beautifully. General relativity predicts the orbits of planets, the bending of light by galaxies, the existence of black holes, all confirmed by observation. But at the smallest scales, challenges emerge. Quantum mechanics says everything is uncertain and discrete at tiny distances. Space-time might be no exception. At the Planck scale, about 10 to the minus 35 meters, quantum effects should become significant. Space and time might become grainy, fluctuating rather than flowing smoothly. This quantum realm would be a realm of uncertainty, with space-time itself potentially varying in ways we don't yet understand. The challenge is that general relativity and quantum mechanics are not yet unified at this scale. When physicists try to apply both simultaneously, the equations become problematic. This incompleteness suggests space-time as we know it mayn't be fundamental, but emerges from something deeper. Some theories propose that space-time is woven from quantum entanglement. When particles become entangled, their properties link in ways that transcend space. Perhaps these connections, spread throughout the universe, help create the fabric we experience as space-time. Severing entanglement might affect the fabric itself. Others suggest space-time emerges from networks of quantum information. Reality at its deepest level might be information. Bits of yes or no, 1 or 0. Space-time would be the way this information organizes itself at larger scales, a collective property that emerges from countless quantum interactions. Loop quantum gravity proposes that space is made of discrete loops, tiny interconnected threads forming a mesh finer than anything we can observe. Time would emerge from how these loops evolve and interact. Space-time wouldn't be smooth but quantized, made of indivisible units at the Planck scale. String theory suggests another possibility. If fundamental particles are tiny vibrating strings, then space-time might be the stage on which strings vibrate, but that stage itself might emerge from string interactions. The geometry of space could be determined by how strings move and interact, rather than being prior to them. Some physicists even question whether time is as fundamental as we assume. In certain formulations of quantum gravity, time seems to disappear from the most basic equations. What we experience as time might be something that emerges, a way our consciousness organizes perceptions. At the deepest level, reality might be somewhat timeless, with past, present, and future existing in a different way than we experience. These ideas remain explorations. No experiment can probe the Planck scale directly. But the fact that space and time become challenging in our equations suggests we're missing something. The stage we thought was solid might be an approximation, something that works well at everyday scales but becomes more complex when examined at the smallest distances. What we experience as space-time, the arena where stars shine and planets orbit, might be like the surface of the ocean, smooth and continuous from a distance but made of countless droplets when seen up close. Beneath the surface lies something deeper, the true nature of reality, still waiting to be discovered. Nothing to carry with you, just rest in the mystery. Quantum mechanics tells us something curious. Particles don't have definite positions until we measure them. Instead, they exist in superposition, a kind of probability cloud where multiple outcomes are possible simultaneously. An electron can be here and there, passing through two paths at once, behaving like a wave that interferes with itself. Only when we observe it does the particle settle into one location. This isn't just theory. Experiments have demonstrated superposition with electrons, photons, even molecules thousands of times larger. Yet no one truly understands what it means. Does the particle physically exist in multiple places? Or is superposition just a reflection of incomplete knowledge? Some interpretations suggest reality branches into multiple versions. Others propose the universe itself is fundamentally uncertain until observed. Whatever the truth, the ability of a single particle to exist in two places at once remains one of the strangest, most peaceful mysteries of the quantum world. The famous double-slit experiment demonstrates this mystery clearly. Send particles, one at a time, toward a barrier with two slits. You might expect each particle to go through one slit or the other, but the pattern that builds up on a screen behind the barrier shows interference, waves overlapping and cancelling. The only explanation is that each particle somehow goes through both slits simultaneously, interfering with itself. This is superposition. Until measured, the particle exists in multiple states at once, following all possible paths. The mathematics describes it as a wave function, a probability distribution spread across space. The particle is not definitely here or there, but potentially everywhere the wave function has value. When we measure the particle's position, the wave function appears to collapse. All the possibilities resolve into a single outcome. The particle appears at one location. But before measurement, it genuinely seems to occupy a superposition of possibilities. Experiments have pushed superposition to larger scales. Scientists have demonstrated it with molecules containing hundreds of atoms. In carefully controlled conditions, these molecules exist in two places at once, behaving quantum mechanically despite their size. The principle seems quite general, not limited to the tiniest particles. What does superposition actually mean? This question has generated numerous interpretations. The Copenhagen interpretation, oldest and most traditional, says particles don't have definite properties until measured. Before observation, they exist in a state of multiple possibilities. Measurement causes reality to choose. The many worlds interpretation offers a different view. When a quantum system is measured, reality doesn't choose. Instead, it branches. In one branch, the particle is here. In another, it's there. Both outcomes happen just in different worlds. Superposition becomes real parallel realities. The pilot wave interpretation suggests particles always have definite positions, guided by a quantum wave we cannot see directly. Superposition is not about particles being in multiple places, but about our incomplete knowledge of the hidden wave guiding them. Yet another view, quantum Bayesianism, treats the wave function as information rather than physical reality. Superposition represents our uncertainty about the particle's state. Measurement updates our information, collapsing the wave function not in reality but in our knowledge. No interpretation is proven. Each has strengths and challenges. The mathematics works perfectly, predicting experimental results with extraordinary precision. But what the mathematics means, what's actually happening at the quantum level, remains mysterious. Perhaps there's something peaceful about this uncertainty. Quantum mechanics works. We can use it to build technologies, predict experiments, understand nature. Yet the meaning beneath the mathematics stays hidden. Reality at its smallest scales is stranger than anything in everyday experience, operating according to rules we can describe but not quite visualize or fully comprehend. Superposition reminds us that the universe is fundamentally different from what we perceive. At quantum scales, the clear distinctions of everyday life, here or there, now or then, this or that, dissolve into overlapping possibilities. And perhaps that's simply how reality is at its deepest level, not definite but potential, not fixed but fluid, a gentle cloud of possibility waiting to resolve. If your mind wants to chase this thought, let it float past. When two quantum particles become entangled, something remarkable happens. Measure one, and you instantly know the state of the other, no matter how far apart they are. Einstein called this spooky action at a distance, because it seemed to challenge the cosmic speed limit. Nothing should communicate faster than light. Yet experiments confirm entanglement is real. Photons, electrons, even small groups of atoms have been entangled and separated by vast distances. The correlations remain perfect. No signal appears to pass between them, yet the link persists. Some physicists suggest this reveals that reality is non-local, woven together more deeply than space and time suggest. Others think there might be aspects we haven't discovered that could explain it. The mystery deepens with every test. Entanglement connects particles in ways we can measure but cannot fully comprehend, linking distant pieces of the universe in a silent, invisible dance. Entanglement begins when particles interact in certain ways. They might be created together, or brought into contact, or measured jointly. Once entangled, they share a quantum state. Their properties become linked, correlated in ways that transcend separation. If you measure one particle and find it spinning clockwise, the other will be spinning counterclockwise no matter how far away it is. What makes this intriguing is the instantaneous nature of the correlation. Separate the particles by meters, kilometers, or even light years. When you measure one, the other seems to respond immediately. Einstein found this puzzling because it appeared to challenge relativity. Information, according to his theory, cannot travel faster than light. Yet entanglement seems to create connections that ignore distance entirely. Experiments have tested this thoroughly. Scientists entangle particles, then separate them by increasing distances. They measure one particle and check whether the other shows the predicted correlation. Again and again, entanglement holds. The correlations are perfect, immediate, independent of separation. Experiments have confirmed this across kilometers, even between satellites and ground stations, yet no signal passes between the particles. This is important. Entanglement cannot be used to send messages faster than light. The correlations are statistical, revealed only when measurements from both locations are compared later. Each individual measurement yields random results. Only when you compare outcomes do you see the correlation. What does this mean? One interpretation suggests reality is non-local. The universe is not made of separate, independent parts connected by signals. Instead, it's woven together at a deeper level. Entangled particles remain one system, even when separated. The separation might be somewhat illusory, a consequence of viewing reality through the lens of space and time. Another view considers hidden information. Perhaps particles carry information we cannot detect, predetermined values that ensure correlations without instantaneous influence. But experiments testing Bell's inequalities have largely ruled out simple hidden variable theories. If hidden information exists, it must be quite subtle. Quantum mechanics treats entanglement as fundamental. The wave function describing entangled particles spans both locations simultaneously. Measuring one particle affects the joint wave function, determining outcomes for both. From this view, entanglement is not mysterious communication, but the revealing of correlations that were always there, encoded in the shared quantum state. Some physicists see entanglement as evidence that space and time are not fundamental. Perhaps at the deepest level, reality is a network of quantum information. Space-time emerges from this network, and what we call distance is a secondary feature. Entanglement then becomes a window into the underlying structure, showing connections that transcend the emergent space between particles. Entanglement is now being used practically. Quantum computers use it to perform calculations difficult for classical machines. Quantum cryptography exploits it to create highly secure communication channels. Yet even as we use entanglement, its meaning remains somewhat elusive. Einstein resisted the implications, believing there must be a more complete description of reality. His famous declaration that, quote, one reflected his discomfort with quantum mechanics' randomness and non-locality. Yet experiments have sided with quantum theory again and again. The mystery of entanglement is peaceful in its persistence. For nearly a century it has puzzled the brightest minds in physics. It works predictably and reliably. We can create it, measure it, use it. But what it reveals about reality's fundamental nature remains open to interpretation. Two particles, separated by any distance, remain connected in a way we can demonstrate but not fully explain. This silent link spans space, joining distant pieces of the universe in a quantum embrace that goes beyond our everyday intuitions about separation and independence. You can let this mystery rest gently alongside you. One of quantum physics' most intriguing discoveries is that measurement affects what's being measured. In the famous double-slit experiment, particles behave like waves when unobserved, creating interference patterns. But if we measure which path a particle takes, the wave behavior vanishes. The outcome changes simply because we looked. Why should this be? One explanation suggests the wave function, describing all possible states, collapses when observed. But what counts as an observer? Is it a device, a conscious mind, or something else? Some interpretations propose that every possibility happens, branching into multiple universes. Others suggest particles only appear definite when information becomes irreversible. None of these ideas are proven. What we know is that the line between observer and observed is not simple. The universe seems to respond to observation in interesting ways, and this mystery remains one of quantum mechanics' most beautiful puzzles. In classical physics, observation is typically passive. You look at something, and it remains essentially unchanged. A thermometer measures temperature without altering it significantly. A telescope reveals distant stars without affecting them. But quantum mechanics works differently. At tiny scales, the act of measurement becomes an interaction that can fundamentally change the system. The double-slit experiment illustrates this perfectly. Send electrons toward a barrier with two slits. Without measuring which slit each electron passes through, an interference pattern builds up, suggesting each electron behaves like a wave passing through both slits simultaneously. But place detectors at the slits to determine each electron's path and the interference vanishes. The electrons now behave like particles, each going through one slit or the other. Nothing changed except observation. The setup is identical. The electrons are identical. The only difference is whether we measure which path they take. Somehow, this measurement transforms their behavior from wave-like to particle-like. What causes this change? The traditional explanation involves wave function collapse. Before measurement, the electron exists in superposition, simultaneously taking both paths. The wave function describes this spread of possibilities. Measurement causes the wave function to collapse, selecting one outcome from many possibilities. The electron becomes localized, definite where it was previously spread out. But this explanation raises deep questions. What constitutes measurement? The standard answer involves a measuring device, something larger that interacts with the quantum system. But where exactly does the quantum system end and the measuring device begin? And if measuring devices are made of quantum particles, why don't they also exist in superposition? This is called the measurement problem. It's remained unsolved since quantum mechanics' founding. Different interpretations offer different answers, but none are universally accepted. Some suggest consciousness might play a role. Perhaps observation requires an aware observer. The wave function collapses when information enters a conscious mind. This view is controversial, seeming to give consciousness special physical status and raising questions about what counts as conscious. The many worlds interpretation eliminates collapse entirely. Every measurement causes reality to branch. The electron goes through one slit in one branch, the other slit in another branch. Both outcomes happen. The observer splits too, with one version seeing each result. Measurement doesn't change the quantum system. It separates observers into different branches experiencing different outcomes. Decoherence offers another perspective. When a quantum system interacts with its environment, the environment acts as an observer, entangling with the system and effectively measuring it. Superposition doesn't truly collapse but spreads into the environment, making it invisible to local observation. The system appears classical not because superposition ends, but because it becomes too dispersed to detect. Yet another view suggests the distinction between quantum and classical is about information. Once information about a quantum state becomes irreversible, encoded in the environment in a way that cannot be undone, the system becomes effectively classical. Measurement is the process of creating this irreversible record. What all these interpretations share is acknowledgement that observation is not simply passive in quantum mechanics. Looking changes what you see. The act of measurement, whatever it truly means, transforms possibilities into actualities, waves into particles, uncertainty into precision. This has interesting implications. It suggests the universe might be participatory. Observers are not separate from observed reality, but participants in actualizing it. The questions we ask, the measurements we make, help determine what becomes real. For everyday life, this remains invisible. Larger objects have already been measured countless times by their environments. Their quantum behavior has decohered into classical definiteness. But at tiny scales, in carefully isolated systems, the quantum world reveals itself as fundamentally different. Observing truly matters there. The mystery remains peaceful and profound. Why should measurement be special? What separates observers from observed? How does information about the quantum world transition into classical definiteness? These questions have no settled answers. They sit at the boundary between the quantum and classical worlds, marking a transition we experience constantly, but cannot yet fully explain. The universe, it seems, responds to observation in ways we can measure, but not yet completely understand. Nothing to solve. Just let your thoughts grow quiet. Gravity shapes the cosmos. It holds planets in orbit, binds galaxies together, governs the motion of stars. Yet compared to the other fundamental forces, gravity is extraordinarily gentle. A small refrigerator magnet can overcome the gravitational pull of the entire Earth. Why this enormous difference? The electromagnetic force, strong nuclear force, and weak nuclear force all operate with tremendous power at small scales. Gravity, by comparison, is remarkably subtle. Physicists call this the hierarchy problem. One possibility is that gravity spreads into hidden dimensions we cannot perceive, distributing its strength in ways that make it appear weak in our three-dimensional world. Another idea suggests the true scale of gravity might be masked by physics we haven't discovered at tiny distances. Despite centuries of study, the gentleness of gravity remains unexplained. This balance is fundamental to how the universe works. Without it, stars and planets might not exist as they do. The mystery of gravity's subtlety is what makes the cosmos possible as we know it. The disparity is striking. Electromagnetism is about 1,000,000 trillion times stronger than gravity at the atomic scale. The strong nuclear force is even more powerful. Gravity's weakness is so pronounced that it's almost negligible for individual particles. Consider a single electron and proton. The electromagnetic force between them is about 10 to the 39th times stronger than their gravitational attraction. Gravity is completely irrelevant at atomic scales. Only when vast numbers of particles accumulate does gravity become noticeable. Planets, stars, and galaxies feel gravity's pull because they contain enormous quantities of matter. Why this difference? It's one of physics' deepest puzzles. The forces appear fundamentally different in strength, yet they're all governed by quantum field theory. Something sets gravity apart, making it uniquely gentle. One intriguing possibility involves extra dimensions. Our everyday experience reveals 3 spatial dimensions: up, down, left, right, forward, back. But some theories, particularly string theory, predict additional dimensions beyond these 3. These extra dimensions might be curled up, compactified into spaces too small to detect. If extra dimensions exist, gravity might spread into them while the other forces remain confined to our 3-dimensional space. Imagine gravity as light spreading from a source. In 3 dimensions, it spreads in all directions, becoming weaker with distance. But if there are extra dimensions, gravity could spread into those too, becoming even more diluted. The gravity we experience in 3 dimensions would be a fraction of gravity's true strength. This idea is testable in principle. If extra dimensions exist at accessible scales, experiments might detect deviations from Newton's law of gravity at short distances. So far, tests have found no evidence for extra dimensions, but the search continues. Another possibility suggests gravity appears weak because we're measuring it at scales far from where its true strength manifests. Perhaps gravity's full strength only appears at energies far beyond what we can produce. At everyday energies it appears gentle, but at the Planck scale, where quantum gravity effects dominate, gravity might be as strong as the other forces. Some theories propose that our universe is a brane, a 3-dimensional membrane floating in a higher dimensional space. Gravity can propagate through this larger space while other forces are stuck on our membrane. This would make gravity appear weak compared to forces confined to our 3-dimensional world. The hierarchy problem connects to other mysteries. Why are the masses of fundamental particles what they are? Why is the Higgs field strength what we measure? These questions may all have related answers, pointing toward deeper physics we haven't discovered. What makes gravity's gentleness beautiful is its necessity. If gravity were as strong as electromagnetism, the universe would be quite different. Stars might compress immediately. Planets might not exist in their current form. The delicate balance that allows complex structures requires gravity to be weak enough that matter can organize gradually over billions of years. Gravity's subtlety allows time for chemistry, for planets to form, for life to emerge. A universe with much stronger gravity might be more intense and short-lived. Our cosmos is peaceful and long-lasting, in part because gravity is so remarkably gentle. The gentleness remains unexplained, a fundamental feature of reality whose origin we cannot yet trace. Perhaps it points toward physics beyond our current understanding, hidden dimensions or scales we haven't accessed. Or perhaps it's simply how things are, a basic fact requiring no deeper explanation. For now, gravity's mysterious weakness sits at the foundation of existence, shaping everything from falling leaves to expanding universes, working patiently and persistently despite its remarkable subtlety. Let this thought drift away like a gentle breeze. General relativity describes the universe with breathtaking precision. Quantum mechanics explains the macroscopic world with remarkable accuracy. Each theory has been tested exhaustively and both pass every experiment beautifully, but they do not agree with each other. When scientists try to describe situations where both gravity and quantum effects matter, like inside black holes or at the universe's birth, the equations become challenging. Mathematical difficulties arise. The frameworks are not yet unified. For decades, physicists have searched for a theory that unites them. String theory, loop quantum gravity, and other approaches offer possibilities, but none are confirmed. Without a unifying theory, we cannot fully understand the deepest moments of cosmic history or the nature of space-time at the smallest scales. This gap between our two most successful theories remains one of physics' greatest peaceful mysteries. Two perfect descriptions that somehow cannot yet speak to each other in all situations. General relativity governs the large. It describes how mass and energy curve space-time, how planets orbit stars, how light bends near galaxies, how black holes form. Every test confirms its predictions remarkably well. GPS satellites must account for relativistic effects to function accurately. Gravitational waves, predicted by Einstein a century ago, were detected in 2015, exactly matching theory. Quantum mechanics governs the small. It explains atomic structure, chemical bonds, the behavior of electrons and photons. It's the foundation of modern technology, from semiconductors to lasers to MRI machines. Its predictions are astonishingly precise, sometimes matching experiments to many decimal places. Yet these two pillars of physics are not yet unified. They rest on different assumptions. General relativity treats space-time as smooth and continuous, a flexible fabric that bends but never breaks. Quantum mechanics treats everything else as discrete and probabilistic, existing in superposition until measured. When you try to apply both simultaneously, challenges emerge. Inside a black hole, gravity becomes so strong that quantum effects should matter significantly. But combining the theories produces mathematical difficulties. The equations become problematic, giving results that don't make clear sense. Similarly, at the universe's birth, everything was compressed into a quantum scale region, where gravitational effects were enormous. To describe the Big Bang's first moments requires quantum gravity, but we don't yet have a complete working theory. The incompatibility runs deeper. Quantum mechanics says you cannot measure both position and momentum with perfect precision, but general relativity requires precise measurements of space-time curvature, which involves positions and motions. The uncertainty principle seems to create tension with relativity's smooth geometry. For decades, physicists have sought a quantum theory of gravity, a framework uniting both theories. String theory offers one approach. It proposes fundamental particles are not point-like but tiny vibrating strings. The different vibrations create different particles. One vibration mode corresponds to the graviton, gravity's quantum particle. String theory requires extra dimensions beyond the three we experience. In its most developed form, it predicts 10 or 11 dimensions total. The extra dimensions would be compactified, curled up too small to detect directly. String theory has mathematical elegance and unifies forces naturally, but it's not yet directly testable. The energies required to probe string-scale physics exceed anything we can currently produce. Loop quantum gravity takes a different approach. It keeps general relativity's framework, but quantizes space-time itself. Space becomes granular, made of discrete loops forming a network. Time emerges from how these loops evolve. Loop quantum gravity makes predictions about the very early universe and black hole interiors, but experimental tests remain challenging. Other approaches exist. Causal set theory treats space-time as fundamentally discrete, like atoms of space and time. Asymptotic safety suggests gravity might remain well behaved at all scales if treated correctly. Each approach has promise, but also challenges. The quest for quantum gravity isn't just academic. Without it, we cannot fully understand black holes, the Big Bang, or the ultimate nature of space-time. We're missing a piece of the puzzle, a deeper layer of reality that unifies gravity with the quantum world. What makes this mystery peaceful is how clearly defined it is. We know what's missing. We can identify where our theories face challenges, and we know what a successful theory must accomplish. It must reproduce general relativity at large scales and quantum mechanics at small scales while unifying them seamlessly. Perhaps the solution will be one of the existing approaches. Perhaps it will be something entirely new, a framework we haven't imagined. The answer remains hidden, waiting in the mathematics and in the deep structure of space-time itself. Until we find it, this gap reminds us that our understanding, impressive as it is, remains incomplete. The universe holds secrets at the boundary between the large and small. Secrets that will reveal themselves when we finally learn to speak both quantum language and relativistic language in a single unified voice. Nothing to hold on to, just breathe and rest. Black holes are regions where gravity becomes so strong that nothing, not even light, can escape. As matter falls inward, Einstein's equations suggest it moves toward a point of extreme density called a singularity, but infinity in equations usually signals that our mathematics may have reached its limits. What truly exists at a black hole's centre? Some think the singularity might be real, a place where known physics no longer applies. Others believe a deeper theory, perhaps quantum gravity, will replace it with something finite, a loop of space-time or an entirely new kind of object. The event horizon seals the interior from view, making direct observation impossible. For now, the heart of a black hole remains one of the most inaccessible mysteries in science. Hidden behind a boundary nothing can cross, waiting silently in the darkness. Black holes form when massive stars reach the end of their lives. When fusion ceases, nothing can support the star against gravity's inward pull. The core collapses, and if the star is massive enough, the collapse continues. The matter compresses into a smaller and smaller region, and gravity at the surface becomes overwhelming. At a certain radius, called the Schwarzschild radius, gravity becomes so strong that even light cannot escape. This boundary is the event horizon. Inside it, all paths lead inward. Outside, escape is possible. The event horizon is not a physical surface, but a point of no return, a one-way boundary in space-time. According to general relativity, the collapse continues inside the event horizon. Nothing can stop it in the classical theory. The matter falls inward, compressing toward the center. Einstein's equations predict it reaches infinite density at a point called the singularity. Here, space-time curvature becomes infinite, and the equations no longer give clear answers. But infinity is usually a sign something needs refinement in the theory. Most physicists believe the singularity is not physically real, but indicates where general relativity stops applying. A theory of quantum gravity should replace the singularity with something finite. One possibility is that quantum effects halt the collapse. Uncertainty and quantum pressure might prevent matter from compressing indefinitely. The singularity could be replaced by a quantum core extremely dense but not infinite. Some theories suggest this core might be a Planck star, matter compressed to the smallest possible scale, allowed by quantum mechanics. Loop quantum gravity predicts that the collapsing matter might bounce, the quantum effects creating repulsion that reverses the collapse. The black hole's interior might connect to a new region of space-time, perhaps even birthing a new expanding universe. The singularity would be replaced by a quantum bridge. String theory offers other possibilities. The singularity might be smoothed out by stringy effects, the extended nature of strings preventing point-like infinities. Or the black hole interior might be described by entirely different physics, perhaps connected to extra dimensions. The challenge is that we cannot observe black hole interiors directly. The event horizon prevents any information from escaping. No light, no signal, no particle can cross from inside to outside. This makes the interior inaccessible to observation, sealed behind nature's ultimate boundary. Some information might escape indirectly. Hawking radiation, if real, carries energy away from black holes, causing them to shrink over immense timescales. This radiation might encode information about the interior, but decoding it remains beyond current understanding. black holes also affect their surroundings. Matter falling toward a black hole heats up, emitting X-rays we can detect. By studying these emissions and the orbits of nearby objects, we can measure black hole masses and spins. But the interior remains hidden. What exists at a black hole's heart is one of physics' most profound mysteries. The equations point toward infinite density, but physics typically shouldn't contain infinities. Something deeper must replace the singularity. Something we'll only understand when quantum gravity is more complete. For now, black holes keep their secrets. At their centers lies a region where space and time cease to make sense in our current understanding, where our best theories face limits, where the universe hides aspects of reality behind an impenetrable barrier. This mystery sits in darkness, patient and silent, waiting for the theory that will finally reveal what lies beyond the event horizon, what truly exists where matter falls and space-time itself seems to reach a boundary. Allow this mystery to fade into the background of your thoughts. When matter falls into a black hole, it seems to disappear. But in physics, information about a system's state is supposed to be preserved. So what happens to the information that crosses the event horizon? Stephen Hawking showed that black holes can slowly lose mass through radiation. But if they eventually vanish completely, where does the information go? If it's lost, quantum mechanics might be challenged. If it escapes somehow, the process is not yet understood. This puzzle, the black hole information paradox, has intrigued physicists for decades. Some suggest information is stored on the event horizon itself. Others argue that black holes might connect to other regions of space-time, allowing information to escape through quantum channels. The fate of information in black holes touches the deepest foundations of reality, connecting gravity, quantum mechanics, and the nature of existence itself in a mystery that remains beautifully unsolved. Information in physics is not just data or facts. It's the complete description of a system's state, everything needed to specify its configuration. A fundamental principle of quantum mechanics states that information cannot be destroyed. It can be scrambled, hidden, or transformed, but not truly lost. The universe preserves information. This principle seems straightforward until you consider black holes. When matter falls past the event horizon, it disappears from view. All information about that matter, its composition, its quantum state, everything seems locked away forever. The black hole reveals only its mass, spin, and electric charge. All other details vanish. This seemed puzzling but manageable until 1974, when Stephen Hawking made a remarkable discovery. Using quantum field theory near black holes, he showed they're not perfectly black. Quantum effects at the event horizon create pairs of particles. One falls in, the other escapes. This escaping radiation, now called Hawking radiation, carries energy away from the black hole. Over immense timescales, Hawking radiation causes black holes to shrink. A stellar mass black hole might take 10 to the 67 years to disappear, far longer than the current age of the universe. But eventually even the largest black holes should vanish completely. Here's the paradox. Hawking radiation appears to be thermal, carrying no information about what fell into the black hole. It seems random, like heat radiating from a hot object. If the black hole vanishes completely and the radiation is purely thermal, all information about everything that fell in would be lost. This would challenge quantum mechanics' fundamental principle. Hawking initially thought information might truly be lost, that black holes could be exceptions to quantum mechanics. But this solution troubled most physicists. It would mean quantum mechanics faces limitations, potentially undermining the foundation of modern physics. Others proposed alternatives. Perhaps information isn't lost but encoded in the Hawking radiation, in subtle ways we don't yet understand. The radiation might appear thermal, but actually carry information in correlations too complex to detect currently. As the black hole shrinks, more information might emerge, encoded in the radiation, especially in the final moments when it disappears. Another possibility involves the event horizon itself. The holographic principle suggests that all information about a black hole's interior is stored on its two-dimensional surface, the event horizon. The interior might be a projection of information encoded on the boundary. If true, information never really goes inside. It's always accessible on the surface. Some physicists propose that black holes don't truly vanish completely. Perhaps they leave behind remnants, tiny stable objects containing all the information. Or perhaps black holes connect to other regions of space-time through structures we don't yet understand, allowing information to escape through quantum channels. Recent work suggests information might escape through quantum entanglement. As particles fall in, they become entangled with previously emitted Hawking radiation. This entanglement might gradually transfer information from inside to outside, encoded in the radiation's quantum correlations. The paradox remains open. Different approaches offer different solutions, but none are proven. What makes this mystery profound is what it touches. It connects gravity, quantum mechanics, thermodynamics, and information theory. Solving it will likely require understanding quantum gravity, the unification of relativity and quantum mechanics. For now, the fate of information in black holes remains hidden. Does it escape through subtle quantum channels? Is it encoded on event horizons? Or does quantum mechanics need refinement in extreme conditions? The answer waits in the mathematics, in experiments we cannot yet perform, in observations of black holes we cannot yet make. This paradox sits at the boundary between what we know and what remains to be discovered. A beautiful puzzle linking the nature of information to the nature of space-time itself. Let this puzzle drift away gently as you sink deeper into rest. When the universe was young, it was a dark, simple place. No galaxies, no planets, only clouds of hydrogen and helium drifting through expanding space. At some point, those clouds came together to form the first stars, ending the cosmic dark ages and lighting the universe for the first time. But exactly how this happened remains somewhat uncertain. These first stars, called Population 3 stars, would have been enormous, hundreds of times the Sun's mass, burning hot and bright, but living only briefly before their dramatic ends. They seeded the cosmos with the first heavier elements. The challenge is we've never seen one directly. They lived and died so long ago that direct evidence is elusive. astronomers search for clues in ancient starlight, hoping to glimpse their influence. The process that sparked the universe's first light remains one of astronomy's most peaceful mysteries, hidden in the distant past. After the Big Bang, the universe spent its first few 100,000 years as a hot, dense plasma. When it finally cooled enough for atoms to form, the cosmos became transparent, but it was also dark. No stars yet existed to light the void. This period, lasting perhaps a few 100 million years, is called the Cosmic Dark Ages. During this time, matter was distributed almost uniformly, with tiny variations in density left over from quantum fluctuations in the early universe. Gravity began working on these variations, pulling matter together in regions that were slightly denser. Over millions of years, clouds of hydrogen and helium gas accumulated, growing larger and denser. Eventually, these clouds became massive enough for gravity to overcome the gas pressure pushing outward. They began to collapse. As they contracted, the centers grew hotter. When temperatures reached about 10 million degrees Celsius, nuclear fusion ignited. The first stars were born, ending the cosmic dark ages. But these first stars were unlike any we see today. Modern stars form from gas enriched with heavier elements: carbon, oxygen, silicon, iron. These elements were created in earlier generations of stars, but the first stars had only hydrogen and helium, the primordial elements from the Big Bang. Without heavier elements to help cool the gas, the collapsing clouds couldn't fragment into smaller pieces as easily. This meant the first stars were likely enormous, perhaps 100 to 300 times the Sun's mass. Their size made them incredibly hot and bright, burning with intensity far beyond anything in today's universe. These giants lived fast and short lives. A star 100 times the Sun's mass might shine for only a few million years before exhausting its fuel. Compare this to the Sun's 10 billion year lifespan. The first stars burned through their hydrogen rapidly, fusing it into heavier elements. When they ended, they likely became supernovae, among the most powerful known. These dramatic events scattered the newly created elements into space, enriching the surrounding gas. Subsequent generations of stars would form from this enriched material, incorporating carbon, oxygen, and other elements essential for planets and life. The first stars fundamentally changed the universe. Their ultraviolet light ionized surrounding hydrogen, making space transparent to ultraviolet radiation. This reionization epoch transformed the cosmos from opaque to clear. Their endings created the first heavy elements, setting the stage for chemical complexity. They may have formed the first black holes, some of which grew into the supermassive black holes we see in galaxy centers today. The challenge for astronomers is that no population 3 stars survive. They all ended billions of years ago. We've never observed one directly. The evidence for their existence is indirect, found in the chemical signatures of ancient stars, in patterns in the cosmic microwave background, in the timing of reionization. Telescopes like the James Webb Space Telescope are searching for their light. The most distant galaxies we observe might contain light from the first stars, shifted to infrared wavelengths. By studying these early galaxies, astronomers hope to detect signatures of population 3 stars. To see the influence of these cosmic pioneers, computer simulations model how the first stars formed. They show clouds collapsing, cores heating, fusion beginning. But the details remain somewhat uncertain. Exactly how massive were they? How did they cluster? How quickly did they enrich their surroundings? The birth of the first stars marks one of the universe's most important transitions, the moment when light returned after hundreds of millions of years of darkness. This cosmic dawn shaped everything that followed, yet the exact process, the details of how those first clouds collapsed and ignited, remain hidden in the deep past, a mystery written in light that has long since travelled far beyond our reach. Nothing to remember, just let the story drift. When we imagine galaxies, we often picture elegant spirals, arms of stars curling outward like cosmic patterns. The Milky Way is one. But why should galaxies take such graceful forms? The answer isn't entirely clear. One idea suggests spiral arms as density waves, like gentle traffic patterns where stars bunch up temporarily as they pass through. Another theory proposes that gravitational interactions between galaxies stir stars into curving patterns. Computer simulations can create spirals, but not with complete certainty about all details. Spirals are common throughout the universe, yet their exact origin remains an area of active study. Why some galaxies become elegant spirals while others form smoother ellipses is still explored. When we look at the night sky and see the Milky Way's graceful arms stretching overhead, we're witnessing one of the cosmos' most beautiful patterns still being understood. Spiral galaxies are remarkably common. About 60% of nearby galaxies show spiral structure. Their arms trace graceful curves, sweeping outward from central regions, often marked by bright blue areas where young stars are forming. Yet the physics creating these patterns is still being refined. The challenge is that spiral arms might not be permanently stable structures. If they were fixed, made of specific stars rotating together, differential rotation would wind them up. Inner parts of galaxies rotate faster than outer parts. Fixed spiral arms would twist into tight spirals and potentially blur within a few rotations. But galaxies have been around for billions of years. Many have completed dozens of rotations, yet spiral arms persist. The solution likely involves density waves. Spiral arms may not be permanent groups of stars, but regions where stars temporarily bunch together. Imagine cars on a highway encountering a slower section. Individual cars move through the pattern, but the pattern itself stays in place. Similarly, stars might move through spiral arms, spending some time in the dense region before exiting on the other side. These density waves could arise from gravitational instabilities in the galaxy's disk. Small perturbations get amplified, creating wave-like patterns that rotate more slowly than the stars themselves. As stars enter a density wave, they slow slightly due to increased gravitational attraction, bunching together. This compression can trigger star formation, lighting up the spiral arms with bright young stars. Another factor is differential rotation itself. The way different parts of the galaxy rotate at different speeds can help maintain spiral patterns through various mechanisms. Combined with self-gravity and gas dynamics, this can sustain spiral structure over long periods. Interactions with other galaxies also play a role. When two galaxies pass near each other, their gravitational pull can create spiral patterns. Tidal forces stretch and compress the galaxies, creating arms that may persist long after the interaction ends. Computer simulations show that even a small companion galaxy can trigger spiral structure in a larger galaxy. Bars contribute too. Many spiral galaxies have central bar-shaped structures. These bars rotate, and their gravitational influence can drive density waves that manifest as spiral arms. The bar funnels gas toward the center, affecting how stars orbit and potentially maintaining spiral patterns. But not all galaxies form spirals. Elliptical galaxies are smooth and featureless, containing mainly older stars with little gas. They likely formed through galaxy mergers, events that disrupted ordered rotation and created more rounded distributions. Why some galaxies maintain the disk structure needed for spirals, while others become ellipticals, depends on their formation history and environment. The exact balance of factors creating spiral patterns, density waves, rotation, interactions, bars, is still being studied. Different spiral galaxies show different structures. Some have tightly wound arms, others loosely wound. Some have two main arms. Others have many. This variety suggests multiple mechanisms may be at work, or that galaxies respond differently depending on their properties. Observations continue to refine our understanding. Modern telescopes can map galaxies in exquisite detail, tracing how stars of different ages distribute across spiral arms. Computer simulations grow more sophisticated, modeling gas dynamics, star formation, and gravitational interactions. Each new study reveals more about these graceful structures. What remains clear is that spiral galaxies are products of rotation, gravity, and time. They're dynamic, not static, continuously evolving as stars orbit and interact. The patterns we see tonight have existed for millions of years but are not permanent. They're snapshots of an ongoing process. Beautiful mathematical expressions of gravitational physics operating on galactic scales. The mystery of spiral formation is peaceful in its ongoing nature. For over a century, astronomers have studied these patterns, mapping them, modeling them, trying to understand exactly how they arise and persist. The answer lies in the subtle interplay of gravity, rotation, and gas, a cosmic choreography that creates some of the universe's most elegant structures. You can release these thoughts now. Let them float away. In 2007, astronomers detected a powerful radio signal lasting only milliseconds. Since then, hundreds more have been found scattered across the sky. These fast radio bursts release tremendous energy in the blink of an eye. What causes them? Some bursts repeat, suggesting ongoing processes like magnetars, highly magnetic neutron stars. Others appear only once, hinting at singular events. But no single explanation fits them all. These bursts travel billions of light years, carrying information about the matter they pass through. They might even help map the universe's structure, but until we understand their source fully, they remain cosmic mysteries. Every so often, the universe sends a brief, powerful signal across the void. We can detect it, measure it, but we're still learning what's speaking. The first fast radio burst was discovered accidentally in archived data. An astronomer analysing pulsar observations noticed a brief, powerful spike that didn't fit any known source. The signal had travelled across billions of light years, arriving from far outside our galaxy. Its intensity and brevity made it unlike anything previously seen. Initially, astronomers weren't sure if it was real or an instrumental artifact, but more were found as telescopes searched for them. By now, hundreds of fast radio bursts have been detected, coming from all directions in the sky. They appear randomly, unpredictably, making them challenging to study. What makes these bursts remarkable is their energy. In just a few milliseconds, they release as much energy as the sun emits in about a year. This requires extraordinarily powerful sources. Whatever produces them must involve extreme physics, objects with immense density and magnetic fields, or significant events releasing huge amounts of energy suddenly. The bursts disperse as they travel through space. Lower frequency radio waves arrive slightly later than higher frequencies, delayed by interactions with free electrons in the intergalactic medium. By measuring this dispersion, astronomers can estimate distances. Most fast radio bursts originate billions of light years away in distant galaxies. Some bursts repeat. One source has been observed flashing hundreds of times, following patterns suggesting it might be associated with a magneta, a neutron star with an extraordinarily strong magnetic field. Magnetas can undergo events that release enormous energy bursts. This might explain repeating sources. But many fast radio bursts appear only once and never again. These might come from singular events, objects, or processes that end in producing the burst. Perhaps they're from merging neutron stars, or stars reaching the end of their lives, or other powerful phenomena that happen once and conclude. The challenge is pinpointing sources. Radio telescopes detect bursts, but initially couldn't localize them precisely. Recent advances using arrays of telescopes have allowed astronomers to trace some bursts to specific galaxies. This provides clues about their origins, linking them to regions of star formation or other galactic features. One possibility is that different types of fast radio bursts have different causes. Repeaters might be magnetars. One-time bursts might be stellar events or mergers. The universe might produce these signals through multiple mechanisms, each creating similar observable signatures. Fast radio bursts offer a unique way to study the universe. As they travel across billions of light years, they pass through gas and plasma, interacting with matter in ways that affect their signals. By analysing how bursts disperse and scatter, astronomers can map the distribution of matter between galaxies, regions too diffuse to see directly. These bursts might even help measure cosmic expansion. If astronomers can determine distances and redshifts accurately, fast radio bursts could serve as cosmic markers, revealing how the universe has expanded over billions of years. This would provide independent checks on other distance measurements. What keeps this mystery peaceful is its openness. Every new burst adds data. New telescopes with better resolution are being developed. Theories are being refined and tested. The answer seems approachable, waiting in the data being collected, in the patterns being revealed as more bursts are found and studied. For now, fast radio bursts remain brief signals from across the cosmos. Their messages carry information about their sources and the space they've crossed, but the full meaning, what creates them, why they flash so brilliantly for just milliseconds, remains partly hidden. The universe continues speaking in these brief pulses, and we're learning to listen, gradually understanding the language of these mysterious cosmic signals. Let this mystery rest alongside the others. Every second, high-energy particles called cosmic rays arrive at Earth from space. Most come from the Sun or distant supernovae, but some carry such tremendous energy that we're still learning where they originate. The most extreme cosmic rays pack remarkable energy into a single particle. They might come from supermassive black holes, active galaxies, or processes we haven't fully understood yet. These particles enter Earth's atmosphere, creating cascades of secondary particles. Observatories track them, trying to trace their paths back to their sources. But magnetic fields in space bend their trajectories, obscuring the clues. Cosmic rays are constant visitors, yet their most powerful examples remain partly unexplained, reminders that somewhere in the universe, nature operates particle accelerators far beyond anything humans can build. Cosmic rays were discovered over a century ago, though their nature wasn't understood immediately. Scientists noticed mysterious radiation that increased at higher altitudes. Eventually they realized these were particles from space, constantly arriving at Earth from all directions. Most cosmic rays are protons, hydrogen nuclei stripped of electrons. Others are heavier nuclei, helium, carbon, iron, accelerated to enormous speeds. They travel near the speed of light, carrying kinetic energy that can be remarkable for single particles. Lower energy cosmic rays come from the Sun or nearby supernova remnants. Shock waves from stellar endings can accelerate particles to high energies. These are relatively well understood, but the highest energy cosmic rays are more mysterious. Some carry energies exceeding 10 to the 20th electron volts. Remarkable energy concentrated in a single subatomic particle. That's comparable to a baseball thrown at considerable speed. For a single particle, this is quite extraordinary. The mechanisms that produce such energies are still being explored. Supernovae alone may not be sufficient. Even the most powerful environments we know, near black holes or in active galaxy cores, face challenges in explaining the highest energy cosmic rays. These ultra-high energy particles are rare. Maybe one hits a square kilometre of Earth's surface per century. But their existence poses interesting questions. Where did they come from? How are they accelerated? One possibility involves supermassive black holes at galaxy centres. The accretion disks around these objects, or the jets they produce, might create conditions extreme enough to accelerate particles to such energies. Active galactic nuclei, galaxies with particularly energetic cores, could be sources. Another idea suggests gamma-ray bursts, among the most powerful events known, might produce ultra-high energy cosmic rays. These bursts release tremendous energy in seconds. The shock waves they create could accelerate particles to extreme speeds. More speculative ideas involve exotic physics. Perhaps these particles are products from processes left over from the early universe, or perhaps they're produced by features in space-time, cosmic structures or other remnants of the Big Bang. The challenge in identifying sources is that magnetic fields throughout space bend charged particles' paths. By the time a cosmic ray reaches Earth, it has been deflected many times, making it nearly impossible to trace back to its origin precisely. The trajectory points toward no specific source. This is particularly challenging for the highest energy cosmic rays. They should be deflected less by magnetic fields because of their enormous momentum. In principle, they could point back more directly to their sources, but even they get bent enough to obscure their origins. Observatories designed to detect ultra-high-energy cosmic rays cover vast areas. The Pierre Auger Observatory in Argentina spans 3,000 square kilometers, using an array of detectors to catch the rare cascades these particles create. When a cosmic ray hits Earth's atmosphere, it produces a cascade of secondary particles. By detecting these showers, scientists can infer the original particle's energy and direction. Despite decades of observations, the sources remain somewhat uncertain. There are hints, possible correlations with certain types of galaxies or cosmic structures, but no definitive answer yet. The mystery persists, patient and quiet. What makes cosmic rays interesting is their connection. They link Earth to the universe's most extreme environments. Each particle arriving has travelled for potentially millions or billions of years, crossing vast distances, carrying energy from events far beyond everyday experience. They're messengers from cosmic processes, from phenomena operating at scales beyond our direct reach. Allow yourself to simply listen and drift. The highest energy cosmic rays remain somewhat unexplained, pointing toward physics or sources we're still discovering. Perhaps future observatories will finally trace them to their origins. Perhaps new theories will reveal how nature accelerates particles to such incredible speeds. For now, they arrive constantly, invisibly, carrying secrets about the universe's most powerful processes, mysteries written in single particles crossing the cosmos. The Big Bang should have created equal amounts of matter and antimatter. When these meet, they annihilate into pure energy. If they'd been perfectly balanced, everything might have vanished instantly, leaving no stars, planets, or light. Yet here we are. Matter appears to have won. Why? Experiments show matter and antimatter behave almost identically, with only tiny differences. These asymmetries may have tilted the balance in the early universe, but they don't seem large enough by themselves to explain why anything exists. Somewhere in the first moments after the Big Bang lies the reason one type of matter survived while its opposite nearly disappeared. This mystery is fundamental. Without it, there would be nothing. The slight advantage of matter over antimatter, the reason something remains, rests peacefully in the cosmic past, still being explored. Antimatter is not science fiction. It's real, and we can create it in laboratories. When a particle meets its antiparticle, they annihilate in a flash of pure energy. An electron meeting a positron, its antimatter twin, converts completely to photons. A proton meeting an antiproton does the same. The process is complete. Total conversion of mass to energy according to Einstein's famous equation. The laws of physics treat matter and antimatter almost symmetrically. For every particle, there should be a corresponding antiparticle with opposite charge but identical mass. The universe should produce them equally. And indeed, when we create particles in high-energy collisions, matter and antimatter appear in equal amounts. This makes the universe's composition deeply puzzling. Look around and you see matter everywhere. Stars, planets, dust clouds, galaxies, all made of ordinary matter. Antimatter is virtually absent. We see no galaxies made of antimatter, no antimatter stars shining in distant space. If such things existed, we'd likely detect the gamma rays from annihilation at the boundaries where matter and antimatter regions meet. We see no such signals. This means the observable universe is overwhelmingly made of matter. The antimatter that should have been created alongside it has vanished. Or more accurately, matter and antimatter mostly annihilated each other in the early universe. But matter had a tiny excess. That excess is everything we see today. Calculations suggest the imbalance was extraordinarily small. For every billion antimatter particles, there were about 1,000,000,001 matter particles. When matter and antimatter annihilated, that one extra particle per billion survived. All the matter in today's universe comes from that tiny asymmetry. But why should there have been an asymmetry at all? Physicists call this baryon asymmetry, and explaining it requires finding differences in how matter and antimatter behave. Three conditions must be met. Processes that change the number of particles must exist. Matter and antimatter must behave slightly differently, and the universe must have been out of thermal equilibrium, preventing reactions from erasing any asymmetry as fast as it formed. Experiments have found small violations of matter-antimatter symmetry. Certain particles called kaons and B-mesons decay slightly differently depending on whether they're matter or antimatter. These violations are real but seem quite small, not obviously sufficient to explain the observed asymmetry. The differences are measured in parts per thousand, not the 1 part per billion needed. Perhaps the early universe hosted processes we cannot recreate in laboratories. At the tremendous energies present in the first moments after the Big Bang, physics we don't yet fully understand might have operated. New particles or forces beyond the standard model could have created the asymmetry. Theories involving grand unification or leptogenesis propose mechanisms, but none are confirmed. Another possibility involves the Higgs field. During the early universe's cooling, the Higgs field might have transitioned through states that temporarily affected symmetry, creating more matter than antimatter. But again, the details remain explorations. What makes this mystery profound is its necessity. Without baryon asymmetry, the universe would contain only radiation. Matter and antimatter would have annihilated completely, leaving photons but nothing to form atoms, molecules, or complex structures. No stars would shine because there would be no matter to fuel them. No planets would form. No life could emerge. The tiny imbalance that allowed matter to survive is responsible for everything. Every atom in your body exists because of that asymmetry. The fact that you can wonder about this question depends on it. Something in the early universe tilted the balance just enough for existence to continue, for now. The exact mechanism remains hidden in the first fractions of a second after the Big Bang. The answer might require physics we haven't discovered, perhaps related to quantum gravity or extra dimensions, or it might be waiting in particles we haven't detected or interactions we haven't observed. The slight advantage of matter over antimatter is written into the structure of the universe, a fundamental feature we can measure but cannot yet fully explain. This mystery sits at the foundation of existence itself, quietly enabling everything that followed. You can let this thought drift away now. Life on Earth began more than 3.5 billion years ago. Fossil evidence shows microorganisms already present not long after the planet cooled. But the details of how life originated remain hidden. How did non-living chemistry cross the threshold into biology? One possibility is that simple molecules self-organized into chains capable of storing information, perhaps RNA before DNA. Another suggests life emerged near hydrothermal vents on the ocean floor, where chemistry and energy combined. Still others propose that life's building blocks arrived from space on comets or meteorites. Scientists have created amino acids and basic molecules in laboratory conditions mimicking early Earth. But producing a fully living system remains beyond current reach. The origin of life may have been one unique event, or it might be a natural outcome when conditions align in the right ways. Until we find clearer evidence, the moment when chemistry first awakened into life remains one of science's deepest, most peaceful mysteries. Earth formed about 4.5 billion years ago from the disk of material surrounding the young sun. The planet's early years were turbulent, with impacts from asteroids and comets delivering water and organic materials. The surface gradually cooled, oceans formed, and conditions stabilized. By 3.5 billion years ago, possibly earlier, life had emerged. The fossil record shows that simple cells existed remarkably early in Earth's history. This suggests life arose relatively quickly once conditions were suitable. But the transition from chemistry to biology remains one of science's greatest puzzles. What steps led from simple molecules to self-replicating, evolving systems? Life as we know it requires several key features. It needs to store information, replicate itself, and evolve through natural selection. Modern cells use DNA to store information, proteins to perform functions, and RNA to connect the two. But this system is extraordinarily complex. It seems unlikely to have emerged fully formed from the start. Many scientists believe RNA came first. RNA can both store information like DNA and catalyze reactions like proteins. This dual capability suggests it could have been life's original molecule. In an RNA world, these molecules might have replicated themselves and evolved before DNA and proteins appeared. But even RNA is complex. How did the first RNA molecules form? Laboratory experiments show that nucleotides, RNA's building blocks, can form under certain conditions. Experiments like the Miller-Urey experiment in 1953 demonstrated that amino acids and organic compounds could arise from simple gases subjected to energy, simulating early Earth's atmosphere and lightning. Subsequent experiments have created more complex molecules, including nucleotide components. But bridging the gap from these building blocks to functioning replicators remains challenging. Something had to organize these molecules, concentrate them, and allow them to interact in ways that led to self-replication. Hydrothermal vents offer one possible setting. These underwater hot springs release mineral-rich water into the ocean. The chemical gradients and energy available might have driven reactions leading to life. The minerals could have acted as catalysts, surfaces where molecules concentrated and reacted. The constant flow of energy could have powered increasingly complex chemistry. Clay minerals offer another possibility. Their layered structure might have provided templates for organizing organic molecules, helping them form long chains and interact in ordered ways. The surfaces could have protected fragile molecules from disruption, while allowing them to evolve complexity. Panspermia suggests life's ingredients, perhaps even simple life itself, came from space. Meteorites contain amino acids and other organic compounds, showing these molecules form naturally in space. Perhaps comets delivered the building blocks, or even primitive microorganisms to early Earth, seeding the planet with life. The challenge with all these theories is evidence. We cannot directly observe what happened billions of years ago. The rocks from that era have been recycled by Earth's geology. The early atmosphere and oceans have changed completely. We're left inferring from what little evidence survives and from experiments trying to recreate early Earth conditions. What makes the origin of life especially mysterious is whether it was likely or unlikely. If life emerges easily wherever conditions are right, the universe might be filled with living worlds. If it required extraordinarily rare circumstances, Earth might be unusual. We don't know which is true. The boundary between non-life and life is not sharp. Viruses, for example, blur the line. They replicate and evolve, but cannot do so independently. Perhaps the first living systems were similarly ambiguous. Proto-life that wasn't clearly alive or not alive, but represented steps along a continuum. What remains certain is that somehow, somewhere on early Earth, chemistry became biology. Molecules began replicating, competing, evolving. From that humble beginning, life diversified, eventually producing every organism that has ever existed. The pathway from chemicals to cells remains partly hidden, a chapter of Earth's history written in molecules that have long since been recycled, leaving only hints of how life first began. Nothing to solve tonight, just rest. Every thought, every memory, every moment of awareness seems to arise from the brain. Scientists can measure electrical signals across neurons, track activity when you focus or dream, even alter consciousness with anesthesia. Yet none of this explains why there is an inner experience at all. Why should neural activity create the feeling of being alive? A brain scan might show activity when you see a sunset, but it doesn't explain why that experience comes with warmth and colour inside your mind. Researchers have ideas. Consciousness might emerge when information integrates across the brain, or when neurons form specific patterns. Some even suggest awareness could be a fundamental property woven into nature itself. but none truly explain the leap from matter to mind. Consciousness is the most ordinary thing. It's what you're experiencing right now. Yet when we try to explain it, the mystery deepens. We know it arises from the brain, but the how remains beautifully hidden. Consciousness is immediate and undeniable. Right now, you're aware of these words, perhaps aware of your breathing, the feeling of resting, the quiet around you. This awareness, this inner experience is consciousness. It's what it feels like to be you, the subjective quality of existence. Science can study the brain in remarkable detail. We can watch neurons signal, track blood flow to different regions, measure electrical patterns across the cortex. We can identify which areas activate when you see faces, hear music, or solve problems. We can even predict what you're thinking about based on brain activity patterns. But none of this explains consciousness itself. Why does brain activity produce experience? A computer processes information without being conscious. A thermostat responds to temperature without feeling anything. What makes the brain different? Why does its information processing come with inner awareness? This is called the hard problem of consciousness. Distinguished from easier problems like explaining how the brain processes sensory information or controls behavior, those are challenging but seem addressable through neuroscience. The hard problem asks why there's something it's like to be conscious, why experience exists at all. Various theories attempt answers. Integrated information. Theory suggests consciousness arises when a system integrates information in specific ways. The brain's billions of neurons form networks where information flows and combines. When integration reaches a certain level, consciousness might emerge. This theory makes predictions about which system should be conscious based on how they process information. Global workspace theory proposes that consciousness involves information broadcasting across the brain. When information reaches a quote too accessible to many brain systems, it becomes conscious. Unconscious processing happens locally, but conscious awareness requires widespread access. Some neuroscientists focus on specific neural patterns. Perhaps certain frequencies of brainwaves correlate with consciousness. Or perhaps consciousness requires feedback loops, information cycling through brain regions in specific ways. These theories identify neural correlates of consciousness, but face challenges in explaining why these patterns produce experience. More explorative proposals suggest consciousness might be more fundamental than we think, not just emerging from complexity. Panpsychism argues that consciousness, or something like proto-consciousness, could be a basic feature of matter. Complex consciousness in humans emerges from simpler forms of awareness present throughout nature. This view is controversial, but addresses why consciousness exists at all, rather than assuming only complex systems like brains have it. Others wonder if consciousness involves quantum effects. Perhaps the brain operates partially at quantum scales, with quantum properties playing roles. This remains highly speculative and controversial, with most neuroscientists skeptical that quantum mechanics is necessary to explain consciousness. What all theories face is explaining the experiential gap. Even if we identify exactly which brain processes correlate with consciousness, even if we can predict and understand it perfectly, we still face the question of why those processes feel like anything. Why is there subjective experience accompanying objective brain function? This gap might be challenging to bridge in traditional ways. Perhaps consciousness is different enough from other phenomena that it requires entirely new concepts, ways of thinking that don't yet exist. Some philosophers suggest consciousness might remain mysterious in certain respects, somewhat resistant to complete scientific explanation in physical terms, yet the brain clearly produces consciousness. Damage certain areas and consciousness changes or disappears. Anesthesia reliably affects consciousness. The correlation between brain and mind is undeniable. What we lack is full understanding of how physical processes generate subjective experience. As you rest here, consciousness continues its mysterious work. Somewhere in your brain, patterns of neural activity create your awareness of this moment. The mechanism remains hidden, perhaps the deepest puzzle of all. The fact that matter can become aware of itself, that the universe has produced beings capable of wondering about their own existence, is remarkable. And yet we still cannot fully explain it. Consciousness remains the most intimate mystery, closer than anything else, yet still profoundly unexplained in its deepest aspects. Let this thought fade as you sink deeper into rest. Every night, your mind creates experiences, some vivid and familiar, others strange and fragmentary. These are dreams. Though universal, their purpose remains somewhat unclear. Some scientists think dreams help the brain process information, replaying memories and strengthening connections. Others believe they help regulate emotion, letting you experience feelings safely. Some suggest they might be neural activity organized into stories. What makes dreams remarkable is their power. They can wake you, move you, or bring insights. Sometimes dreams even contribute to problem solving, bringing understanding that eludes waking thought. The brain remains active during REM sleep, when most vivid dreaming occurs, but why it creates these nightly journeys remains an open question. Dreams are familiar experiences, yet their meaning drifts just beyond full understanding, a mystery you visit every time you close your eyes. Everyone dreams, though not everyone remembers. Throughout the night, your brain cycles through different sleep stages. During REM sleep, rapid eye movement sleep, brain activity increases significantly. Your eyes move beneath closed lids. Your muscles relax almost completely, preventing you from acting out dreams. And you dream, experiencing scenarios that feel real while they last. Dreams have fascinated humans for millennia. Ancient cultures saw them as messages or glimpses of other realms. More recently, various thinkers proposed they revealed unconscious processes or contained symbolic meanings. Modern neuroscience approaches dreams as brain activity, but their purpose remains explored. One theory suggests dreams help consolidate memories. During sleep, the brain might replay experiences from the day, strengthening important connections and organizing less useful ones. Dreams might be side effects of this process, fragments of memory activation organized into narratives. Studies show that learning improves with sleep, particularly REM sleep, supporting this idea. Another view emphasizes emotional regulation. Dreams often involve emotional situations, concerns, desires. Perhaps they provide spaces to process feelings without real-world consequences. You can experience various emotions in dreams, and upon waking, you're safe. This might help the brain work through feelings, maintaining psychological balance. The threat simulation theory proposes dreams might have evolved as practice for challenging situations. By experiencing various scenarios in dreams, our ancestors might have prepared themselves for real challenges. Though modern life differs from ancient times, the mechanism could persist, creating scenarios where we face and work through difficulties. Some researchers think dreams may not have a specific purpose. Perhaps they're patterns, neural activity during sleep that the brain's narrative capacity organizes into stories. We're good at finding patterns and creating meaning, which might turn a random activity into coherent dreams. Yet dreams often feel meaningful. They can be emotionally intense, sometimes more vivid than waking life. Some contain insights. Various creative breakthroughs have been attributed to dreams, though these are anecdotal. Such accounts suggest dreams sometimes access processes unavailable during waking thought. The content of dreams varies enormously. Some replay recent events quite directly. Others combine elements from different times and places, creating surreal scenarios. Common themes like flying, falling, or appearing in public, unprepared, suggest shared processes shaping dream content. Lucid dreaming, where you become aware you're dreaming while still asleep, adds another layer of mystery. Lucid dreamers can sometimes influence their dreams, making choices about where to go and what to do. This suggests consciousness can be present in different forms during different sleep states. REM sleep isn't the only time we dream. Studies show dreaming occurs during other sleep stages too, though these dreams are often less vivid and less remembered. The brain never fully shuts down. It remains active, processing, organizing, creating. What we're still exploring is a complete theory explaining why we dream. We know dreams correlate with REM sleep. We know they involve activity in visual, emotional, and memory-related brain regions. We know they reflect our experiences and concerns, but the deeper purpose, if there is one, remains somewhat uncertain. Perhaps dreams serve multiple functions, consolidating memory, regulating emotion, simulating scenarios, processing experiences. Perhaps they're necessary for brain health in ways we don't fully understand. Or perhaps they're beautiful patterns, meaning emerging from neural activity, stories we tell ourselves while the brain performs its nightly maintenance. As you drift towards sleep tonight, your brain will begin its nightly cycles. Dreams will come whether you remember them or not. They'll carry you through landscapes of memory and imagination, through emotions and scenarios your waking mind might never construct. And in the morning, most will fade, leaving only fragments, or nothing at all. The purpose of these nightly journeys remains a gentle mystery, visited by everyone yet understood incompletely. Let yourself drift now, nothing to remember. Science has carried us far. We've mapped galaxies, decoded DNA, explored distant worlds. Each answer reveals new questions. Each discovery opens deeper mysteries. Perhaps one day we will explain consciousness, the origin of life, the birth of the universe, the nature of time itself. Or perhaps some mysteries will always remain just beyond complete reach, woven into the fabric of existence in ways we cannot fully untangle. The greatest mystery might not be any single question, but whether human minds can ever fully comprehend reality's totality. As you drift towards sleep, you might hold this thought gently. Curiosity itself is part of the mystery. To wonder is deeply human, and to seek is to be alive. The questions may never end, but neither will our search, and perhaps that's the most beautiful mystery of all. Look at how far we've come. A few centuries ago we thought Earth was the centre of the universe. Now we know it's a planet orbiting an ordinary star in one galaxy among billions. We've sent robots to Mars, photographed distant planets around other stars. Our knowledge has expanded beyond anything our ancestors could have imagined. We've decoded the human genome, understanding the molecular instructions that build and maintain life. We've explored atoms, revealing the quantum world. We've detected gravitational waves, ripples in space-time itself. We've traced the universe back to its first moments, mapping cosmic history across billions of years. Each breakthrough seemed impossible before it happened. Flight was a dream until it was achieved. Atoms were speculations until we could image them. Black holes were mathematical curiosities until we photographed one. Science repeatedly achieves what seemed unreachable. Yet mysteries remain. We've explored many tonight. Dark matter and dark energy make up most of the universe, yet we don't know what they are. Quantum mechanics works perfectly but defies simple explanation. Consciousness arises from brains, but we cannot fully explain how. Life began somehow, but the details remain hidden. These mysteries might be solvable. Perhaps the next decade will identify dark matter. Perhaps quantum gravity will unify physics. Perhaps neuroscience will deepen our understanding of consciousness. Each could happen, extending human understanding further into the unknown. But some questions might never have answers we can fully grasp. Perhaps consciousness is inherently challenging to explain in purely physical terms. Perhaps the universe's origin lies beyond direct scientific inquiry, because it involves the creation of space and time themselves. Perhaps some truths are somewhat inaccessible to minds like ours, shaped by evolution for survival, not cosmic comprehension. This raises a profound question. Are there limits to human understanding? Are we capable of eventually knowing everything, or will reality always exceed our grasp somewhat, containing layers beyond what minds can fully fathom? Our brains evolved to navigate social groups and physical environments. That we can understand abstract mathematics, quantum physics, or cosmology is remarkable. These weren't survival skills for our ancestors, yet somehow human minds can comprehend atoms, galaxies, and forces far beyond everyday experience. But comprehension may have limits. We cannot easily visualize more than 3 dimensions. We struggle with quantum superposition intuitively. We find infinity conceptually challenging. Perhaps these limits reflect real boundaries on human cognition. Perhaps some truths require ways of thinking we don't possess and cannot easily develop. Or perhaps future humans, perhaps enhanced by technology or evolution, will transcend these limits. Perhaps artificial intelligence will understand things we cannot. The search for knowledge might continue far beyond current humanity, carried forward by whatever comes after us. What remains certain is that curiosity drives us forward. We wonder, we question, we seek answers. This impulse has shaped human history, driving exploration, invention, and discovery. Even knowing some questions might be very challenging doesn't stop us from asking. There's something beautiful about this. We're small, temporary beings in a vast, ancient universe. Yet we can contemplate that vastness, ask why it exists, marvel at its complexity. The fact that matter can organize itself into forms capable of wonder is perhaps a deep mystery itself. Science is not a collection of facts, but a process, a way of asking and answering questions. It progresses through curiosity and testing. Each generation adds to knowledge, building on what came before. The search continues, patient and persistent. Tonight, you've journeyed through mysteries spanning cosmology, physics, biology, and consciousness. Some may be solved in your lifetime, others might remain open for centuries, some might never be fully answered, but each one represents a question worth asking, a puzzle worth contemplating, a reminder that reality is richer than we yet understand. As you rest now, let these mysteries drift away gently. There's nothing you need to solve tonight. These questions have waited billions of years. They can wait a bit longer. The universe continues its quiet unfolding, patient and timeless, holding its secrets close while slowly revealing them to those who seek. The search for understanding is humanity's greatest adventure. It may never fully end. And perhaps that's exactly as it should be. A universe completely understood might lose some of its wonder. A cosmos full of mysteries invites endless exploration, endless discovery, endless awe. The questions themselves are gifts, invitations to wonder, reminders that existence is far stranger and more beautiful than we yet realize. And now the mysteries begin to gently fade into the background of your thoughts. You have drifted through so many unanswered questions tonight, from the birth of the universe to the nature of consciousness, from invisible influences shaping galaxies to the origins of life itself. You have explored black holes and quantum particles, spiral galaxies and fast radio bursts, the gentleness of gravity and the puzzle of antimatter. Each mystery an invitation to wonder, each question a doorway to calm reflection. These are not problems demanding solutions tonight. They are simply part of the universe's quiet beauty, reminders that reality is richer and stranger than we yet understand. Some of these mysteries may be solved in your lifetime, others might wait centuries, some might remain forever open, and that is perfectly fine. The universe has been patient with its secrets for billions of years. It can wait a little longer. You are part of this mysterious cosmos. The atoms in your body were forged in ancient stars. The questions you can ask arise from the same matter and energy that fills galaxies and lights distant suns. You are connected to all of it, held gently within existence itself, resting peacefully among mysteries that span from the smallest particles to the vastest reaches of space. Tonight, as you drift into sleep, the universe continues its quiet unfolding. Stars are shining, galaxies are turning, quantum particles are dancing their strange dances, and somewhere perhaps answers are waiting to be found, but not tonight. Tonight is for rest, for letting go, for allowing these gentle mysteries to carry you softly into dreams. There's nothing you need to remember, nothing you need to solve. Just let your breathing slow and your body grow heavy. The mysteries will still be there tomorrow, patient and peaceful, waiting for those who wish to seek them. But for now, they ask nothing of you except to rest. Thank you for journeying through these beautiful unknowns tonight. May you sleep deeply and peacefully, held safely in a universe full of wonder. Good night.